Hi, everyone. Welcome to my podcast. And today I'm really honored to introduce you Tan Jie. Jie is one of the most famous researcher in robotic AI industry and is leading Gemini robotic team. Maybe Jie can make a quick self-introduction about like your background, what have you been doing even before like Gemini and all that.
Thanks for the introduction. Hello, everyone. My name is Jay, and I'm currently a research scientist at Google Deepmind and working on robotics. And currently, I'm leading Deepmind Robotics, which is a robot foundation model specific for robot manipulations. I have been in robotics or Google working on similar topics for roughly 10 years. Before that, I'm really a person like computer games. So my PhD is around computer graphics. And at a certain time, I feel that computer graphics is amazing, that allows you to simulate a lot of things that you see. But I really want that my influence can be beyond the virtual world, can go out of the screen to make it more tangible. So maybe in the last 2 years of my PhD, I talked to my advisor. I said that I want to use these technologies that we developed in simulations, in graphics, to see whether it can revolutionize robotics. So that's when I entered the robotics field. Right after my graduation, I worked in a startup for a short amount of time. It's called Litro, and it's I'm working on the light field cameras. And after that, I joined Google. As I mentioned that I want to use the technologies in graphics to change robotics. And the first paper I did at Google is called Sim to Real, Learning Agile Locomotion for Quadruped Robots. So that's one of the early papers that used deep reinforcement learning to control robot locomotion. And the technology I developed exactly is simulation to the real world. And this is end up as one of the very important paper in the history of robotics, because nowadays, everyone who work on locomotion, whole body control is using reinforcement learning simulation and adopt a very similar technology to map the policies from the simulation world to the real world. So after that, I work more and more on navigation, and then nowadays, the robot foundation models.
Wow, thanks so much. That's a really interesting introduction. Yeah. By the way, I also used to work at Google, at that time called Google Brain, of course, now DeepMind in 2016, and have honor to kind of being in the same time with a lot of the interesting people like Sergey and also like Chelsea Finn, where they were working on the early days of robots. So I think Google's robotic is probably the longest like a duration research lab, right? It spans almost 10 years.
Yeah.
That's kind of amazing.
Exactly, especially for this relatively new field of robot learning. Our lab is definitely like pioneered a lot of the research and technologies that we are using today. As I mentioned, that the deep reinforcement learning is one of the paradigm shift in the last 10 years. And the second paradigm shift, probably from my perspective, is robot foundation models. Again, our team pioneered some of these early technologies, such as SeiCan, such as RT1, RT2, and nowadays to Gemini Robotics.
Yeah. Okay. So I guess the first question, let's go like a bird eye view on the industry. What do you think is the biggest breakthrough that accelerates embodied AI in the last 3 years? Anything other than like a foundation model that really amazed you?
Yeah. I think that maybe let's extend the horizon a little bit from 3 years to maybe 5 years.
Yeah.
As I mentioned, actually, in your first question, I think there are two major breakthroughs. The first one is deep reinforcement learning that has revolutionized the entire locomotion whole body control, no matter it's for quadruped robots or for the bipedal humanoid robot. I'm going to dive a bit more into the details. But the second paradigm shift is really robot foundation models that nowadays a lot of the research community has converged to this direction. So let's talk about deep reinforcement learning a little bit more. So before deep reinforcement learning, when people control Lego robots, they use a method called MPC, Model Predictive Control. And the most famous company doing that is Boston Dynamics. They are pretty secret, so nobody actually know what they do to show all those amazing videos.
Yeah, even if they work at Google before.
Even though they work at Google before, actually, very few people know the underlying technology until very recently. In the last couple of years, they start to be more open and discuss the method behind it. So MPC is very complex. You need to build a mathematical model for the whole robots and its interaction with the world. And then you need to use an optimization technique to solve it. And there's a lot of constraint restrictions how this method can be applied. So I often say that you will need a PhD degree to understand MPC totally. And to work in this area. But like five to maybe 6-7 years ago, deep reinforcement learning becomes really popular. This is because AlphaGo, developed by Deepmind, shows the power of reinforcement learning, and people naturally ask, can the same technology apply to control robots? I think I'm fortunate to join Google at that time, where sort of pioneered this technology and application in robotics. And since then, it becomes so popular. Like almost every company use reinforcement learning to control bipedal and quadruped robots. There's a bipedal robot can run, they can jump, they can parkour, they can boxing, they can dance, they can do all kinds of amazing techniques, motions. And all these techniques I think, stem from the initial innovation like 7 years ago. And even today, I believe that Boston Dynamics has ditched the traditional MPC technology and fully migrated to reinforcement learning. I think this is really a huge breakthrough that has changed the entire field of robotics. Okay, so that's the first paradigm shift that has happened in the last 7 years. As I mentioned, the second paradigm shift is robot foundation models. I think it starts from really when we see the large language models start to become more and more general, and the generality is really one of the bottlenecks for robots. Robots need to generalize to different scenarios before they can enter and operate in our very complex, diverse world. And then people think, can we leverage the generalization of language models and use them to control robots? So some of the early paper like SayCan basically leverage the common sense of the language models for robot to plan for complex tasks. So traditionally, you have to program the robot, right? So you need to write like C++ or Python so the robot can do exactly what you want it to do. And again, the entry barrier of robotics is very high. But today, you can just talk to the robot using natural language. You say, I want a coffee. Robots don't understand coffee, right? So, but the language model, which acts as a brain of the robot, understand what it means to make a coffee. What are the steps to make such a coffee? So SayCan, the paper, basically leverages this idea to use language model to decompose these very complex tasks to simpler like primitives, and then ask robot to execute all these motions. So after that, people start to fine-tune these language models, or today, like multimodal large foundation models, such as vision language models, and make it to output actions. Gemini robotics is such an example, so that robot now really have the brain to understand the world. It has a world knowledge, it has a common sense, and now it can generate actions to accomplish a lot of tasks you ask it to do.
Yeah. I think that's really interesting, and feel really like familiar with the whole history, right? I think Moyan is part of the SayCan thing, and have saw the early development. And in fact, my PhD is actually from the more like a model predictive control school. One of my PhD advisors is Stephen Boyd, who is a convex optimization guy. It's all about model predictive control. And my previous work life is like in quant finance, where we predominantly use model predictive control for portfolio optimization, multi-horizon planning. And we kind of do not trust the deep RL until very recently, because there needs to be like compliance requirements of what constraint you cannot break, and we need a lot of these things. And of course, people try use like deep RL to actually train to essentially distill the policy that's generated by model predict control, but are slower. Yeah. So I guess the first question I want to ask is on the control side.
Mm-hmm.
Do you see today's deep RL basically following the paradigm of, okay, here are like iterative QR, quadratic programming, or like say model predict control, very complex problem. It like is mathematically still good, but it's just like too slow, and it has like rough edges, movement are too rigid. So with deep RL, you can basically use that as your imitation learning target to start with, and then somehow generalize overall. People just go kind of end to end with a very fresh simulation environment and just learn the policy from ground up.
That's a great question. So usually when people think about, can we marry control with learning, people have two methods, right? The first method is what you said, whether we can use MPC as to generate like trajectories, to generate the initial thing that the RL can sort of imitate, right? So basically it seeds the RL into a good regime of the trajectory space, and then RL is going to do self-improvement to make it much, much better. So that is one way, yes. So that is still a great technique to seed the RL. And even if you don't have MPC, people often use expert demonstrations to seed RL, so that RL does not do exploration in a space that is so far away from the solution. So yes, to your question. And the second technique people usually combine control and learning is that they use reinforcement learning to output some of the parameters of your MPC. Right? So this could be some like a reference trajectories. It could be some parameters in your problem setup. We actually tried this technology before. So before we go all in like an end-to-end RL, we use RL to control MPC. That's a great intermediate stepstone, I would say. But it seems that the entire field have figured out that end-to-end RL is much better. It's more direct. It's more efficient. It also is not always live in the space of the MPC, so it has more freedom to do better control. So I would say that use RL to control the MPC was tried extensively before, but people seems to now shift more towards end-to-end RL, even though this RL can be seeded by MPC.
Yeah, that's totally understandable, right?
Yeah.
In some sense, if you have a multi-horizon planning task, when you roll out the policy, it's in some sense, if you treat the conic program as like a function map, it's essentially like an iterative map. So it's almost like a recurrent neural nets. And some of my PhD work is along this line.
Cool.
So it's interesting that some of those are being re-picked up in completely different contexts.
Yeah.
So I'm curious, from that point of view, it's natural to understand, right? If you roll out the policy, it's still rigid, it's still subject to one function map. So it makes sense to kind of morph it into a more free space to solve it. But how far do people like move away from this like a rigid but mathematically principled policy? In the case of say like Go, right? It turns out AlphaZero, which is completely abandoned of the like a human expert knowledge, turns out to be better. Does anything like this happen in robotics?
I don't think so. It has not happened yet, right? So I think robotics has a lot prior, because if you see robots motion, it's probably you can map it from, oh, this looks similar to how dog runs or how human take actions. So very often the reference provided by human demonstration or MPC is very good. So IO only need to find a better solution in the vicinity of the reference trajectory. But I can see that in the future, if you really want superhuman intelligence or superhuman control, then the IO need to veer away from these reference trajectories. I believe that they might come, but we are not quite there yet.
I see. So you think it's mostly because of the same real gap, right? If you have a real environment that you can train, like roll out a million trajectories, some method like AlphaZero might work, right? Do you feel like if you do this from sim, where assume you can afford enough compute to do like a crazy amount of rollout, like in the AlphaZero case, the most hard scenario is can you find the right family of simulator that covers the real scenario?
So this is a great observation. I think the reason, there's multiple reasons. One is sim-to-real, as you mentioned, because the IO algorithm can exploit the simulation.
Yep.
So it can converge to something makes sense in simulation, but totally doesn't make sense in the real world. So in early days of open AI gym environment, there is an environment called Humanoid, and it's trying to run a obstacle course as fast as possible. So you see that it can run like super fast, superhuman performance, but it comes with all kinds of weird exploitations. Like the humanoid is running with all the waving arms and so on. So it means that if you start from scratch, away from any reference trajectory, it can converge to a local optima that is undesired for real world robotics. So that's one reason. The second reason is really, you can also try to do things in the real world directly, so that you can totally, eliminate the sim to real gap. But I think the RL algorithm is not efficient enough yet to perform in the real world. So I think there are two paths: the sim to real path, but it can exploit simulation, so that make end-to-end RL or IO from scratch infeasible. Then do it in the real world and learn from scratch is not data efficient enough. You probably need to wait for years before the RL policy converge to something that is usable.
Yeah. So in the early days of machine learning, there are interesting ideas like this game theory idea, like GAN, right? Do you see people have already figured out any way to do this, like a generative sim, train a policy? Okay, it's reward hacking. Let's improve the generative sim to make it closer to real and iterate up.
Yeah, so there's something very similar to that. I think in the RL world, there's a paper called adversarial RL. Basically, the idea is that you have some initial simulation, you train in it, then you adversarial add perturbations, you adversarially change the physical parameters, and then you train the policy against it again. This makes your policy more and more robust. It covers a wider area of the physical parameters. So so you are improving your simulation, and then you are improving your policy against it, and so on and so forth. This iterative process definitely is one of the mainstream technology in reinforcement learning today.
Yeah, but people are still using the fixed physical model. It's not like, okay, there's reward hacking on here, I need to add some aerodynamics, I need to add some friction model. So like make a simple simulation to like slowly improve towards a complex simulation.
I see. I have seen some paper, similar towards that directions. One is not necessarily adding a component. It might be just changing the physical parameters. So it's like doing system identification along the way. But yes, there are also like adding more neural networks to model some of the phenomena that is not yet captured in simulation. I think like one of my collaborator, Erwin Kumans, had a paper along that vein.
Oh, that's so cool. Yeah. Since you mentioned you also like to play games, right? How much do you think today's game simulation engine like Unreal family can help in building those like real physics? Oh, it's very far away. It's more good looking.
Okay. Actually, a lot of the physics simulation we are using in robotics today are from computer graphics. The Bullet or PyBullet is basically a engine for like animation and so on. The Erwin, who is the creator of Bullet, won the Academy Award for Science and Technology. So it shows you that these physical engines, even though we adapted to robotics, actually plays a very important role in games and the movie industry. Similar like Mujoko start also from the graphics community, and then it start to play a very important role in robotics. Back to your question on game engines like Unreal, I actually have a couple of papers that learn navigations in Unreal environment. I think one problem of these very sophisticated game engine is it requires someone to build the realistic environment for you, right? It's like you need to design a game to build the indoor environment. So these are very manual process. The second thing is realistic rendering, as many of the games requires, is very expensive to do on computers. For example, if you want a rendering, you can be as fast as real time. That's probably the best you can do. But if you chop off the rendering and only use like OpenGL or more faster rendering techniques, and then your physics simulation can be orders of magnitude faster than real time. And this faster speed is really important for reinforcement learning.
Yep.
Because reinforcement often needs to take in real time, years or hundreds of years of experience in order to learn a good policy.
Yep.
So you really need something much, much faster than real time.
Mm-hmm.
But rendering is really slow nowadays.
I see. So basically, there needs to be an orthogonal style of simulation that can decompose the good looking from the realistic physics, the friction, the touch, whether it's rigid body, and the people haven't built such a good orthogonal thing. Yeah.
So there are actually orthogonal things. So basically, what people often do is they do reinforcement learning in a fast physics engine without rendering. So they do it in the state space, state action next state. Then they sort of use this as a teacher to teach a student that can look from the real observations, which is these rendered image, to the actions. So it's a two-stage, because reinforcement is slow and the data inefficient. You do it in the simulation with only physics. Then we know imitation is very effective. Then you can, then distill your rendering and end-to-end, observation to action policy using imitation learning. So there are these orthogonal divisions of labor using different type of simulations.
I see. So here comes a natural question. If you buy real world gaming assets, or buy say video data plus gaming assets, where some of the real data is probably more realistic, but of course it's given some fixed trajectory. Gaming assets the simulation environment, or some for example, how race cars run in the best race car games. It's probably relatively usable in terms of those companies also try very hard to mimic real world, right?
Yeah.
Is that the kind of a major budget spending place? Just like how when you train large language model, you buy those coders reasoning trays to improve your model. Has we got there in robotics that this data actually matters?
So the data you mentioned is game asset.
Yeah, game asset, and also some real data to calibrate, right? Real data outside of video is normally very limited, unless it's some robotic companies specifically collect.
Right.
So
I think that we are at the verge to explore that direction. But today we do buy a lot of simulation assets or game assets. Then people manually, estimate how heavy this is, where the center mass, then input them into the URDF file, which is a file that the simulation reading to determine the physical properties. So that's where I think the field is mostly today. But there are a lot of research, frontier research, that's trying to figure out how to map from a video to a simulatable asset. But that's still, I would say, a bit early. So it's mostly in research, not in practical implementation yet.
I see. Okay. Yeah, I guess this is interesting where in the next few years, there might be a scenario where robotic data industry will rise to the point of today's kind of coding data, which is kind of Surge is making $1 billion.
I think so. I think that one of the bottleneck in robot learning today is really data, right? So, people now painstakingly actually collect a lot of teleoperation data. So you basically use a teleoperated device and there's a robot next to you. Then you control the robot to pick up objects and so on. And then these data are used to train robot foundation models. It's a very expensive data to acquire because you need a robot and you need a human. And sometimes through the teleoperation device, it's not so transparent. So your motion is much slower than compared to you actually doing it yourself. So I think that in the next few years, people are going to figure out how to leverage different type of data, more scalable data, such as videos, such as simulations, so that we can break the barrier of data. And then we are really enter a stage very similar to large language models.
I see. That's very interesting industry insight. I think people who are listening, maybe it's time to start your robotic data company. Yeah, it's interesting. I think early last year, I asked you about this, had this semi-research, semi-startup idea. People have like already buying these glasses like Meta Ribbon or like Vision Pro. And I think your hand is kind of like one type of like humanoid example. A human is like the prototype humanoid, and if you collect the human data in very extensive way, like for example, you have like less good sensors like Meta Ribbon glass, but you have high-end stuff like Meta have the expensive one that is for research, right? And also Vision Pro have like a very good hand tracking. And recently Meta also have the like a kind of neural band that like tracks your kind of muscle electronic signal. So at some point, I feel like this path is a scalable path, since there are so many human beings that have free time to actually do fun things like show how I'm cooking, so that the cooking data becomes relatively refined trajectories that robotic can learn. But when I ask around all the robotic researchers, it's too early, it's not going to work. Yeah, one of our like a PhD friend, Danfei, I think collaborated with Meta on some of this to extend the, I think it's like Ergo 3D series of work where they put some important like milestones there, but it seems still not like commercially viable direction, right?
So it's a great question. Actually, I was talking to Danfei just right in the airport from Koro to Shanghai about exactly that topic. My feeling is, so first of all, there are two barriers in data collection. One is you want to really scale up the data. The second is how you can leverage these data. Right? So to scale up data collection, I think using glass is a very natural way to do it. At Google, we call it sensorized human data collection. So it's not really collect data through teleoperation, but you sensorize the human. You put the glass on, you sometimes put the glove on, but the human is doing the action by itself, not through a robot. And this data can be easily scaled up if the glass becomes cheap and everyone have a glass. So that can break this scalability barrier. But the second barrier is how you leverage this data, right? So in teleoperation, the data is straightforward. You have the observation from the robot, and you have the action, basically the motor angles and so on from the robot. Then you can create a direct mapping through a neural network that maps the observations to actions. So that's very simple. But now you have these data of human doing things. So it does not look like a robot. So visually, there is a gap. And also, humans' construction of the elbows is different from robots' construction of the elbows, right? If it's humanoid, maybe it's closer. Maybe if it's not humanoid, so the configuration space or the joint degree of freedom are very different. And then all these, how can you transfer from the human data to the robot? And also, you might miss some of the actions. Because the robot, the action is motor angles. And here you only have the visual clue where the hand is. So there's another mapping in action space. So I feel that we have made a lot of progress, especially at Danfei's group in Georgia Tech, how to transfer these sensorized human data to robots. But still, I think it's relatively early stage research. I think that we are going to have a breakthrough in a year, maybe sooner than that. So if that happens, if the glass becomes cheap enough, I think that we are going to get gazillion of data, and then robotics is going to have a great breakthrough.
Yeah, that's really exciting to hear. So today, basically, it's like the better like the machine learning approaches are, your data requirement get lower, right? At some point, you can even use GoPro on top of human from YouTube, and it can teach. It's basically, there is a hierarchical thing, right? Like when you have the most stupid imitation learning, you need precisely the same
data.
Like robots being controlled by experts. And I think you guys worked on RTX, which is like a kind of do the basic cross embodiment, and this is like a very hard cross embodiment,
right?
And basically from very rigid body to human.
Exactly. So I want to add additional comments on what you say. So in robot learning, people often refer to a pyramid of data. So at the bottom, these are very noisy, scalable data sources. These things like a human videos. We already have a lot of data source, but it's cross the embodiment, as you say, from human to robots. Above that, maybe it's a sensorized human, so that you add additional sensors on human. So it's harder to collect these data, but it's still relatively scalable. On top of that, it's maybe simulation, right? So you still need to create a simulation asset. So it's still, there are some like work to do, but simulation is more like compute. Given enough computing and generate the data. And on top of that, maybe it's the teleoperation data. So it's a pyramid. So you can use the more scalable data source that is more noisy in pre-training. So the goal of pre-training is to really get the intuition of physics, intuitive physics, but not precise like control of each robot. But at the bottom, once you have a more precise data like teleoperation, you don't need a lot of these data. But these data is more like a calibrate your robot, understand your robot calibration or joiner configurations, so that you don't need so much of the data. So I think this pyramid is going to give you different ways or different layers to build your robot foundation models.
Do you think this like a training process over the pyramid map also to kind of high level planning towards low level control? In some sense, the highest level is like understanding the world, right? The world models, like kind of observe and plan steps, kind of like the like vision plus kind of secant level things, and then like when you go like into the like specific embodiment, it goes to like nitty gritty control, like whether this arm can generate this amount of friction to pick up something.
Yeah, exactly. I think that this pyramid really shows you need understanding, then you need a very precise control.
Okay. So understanding is something that people have been pushing the most, since it's like mostly kind of can borrow the strengths of the foundation model breakthrough, right? People have made a tremendous foundation model breakthrough, and we can see FSD 11 to 12 to 13 to 14, each is like a massive step function improvement.
Indeed.
Yeah. Do you see some of the other robotic problems, for example, like local motion stuff, all kind of benefit from similar scenario where it's almost getting to be solved like FSD?
Okay. I think that, so first of all, for FSD, it's a different type of understanding compared to manipulation. So for FSD, it's about understanding your environment. It's more about the visual, spatial understanding. And the foundation models we have today, like vision language models, they usually have pretty good understanding of these type of things. But the real understanding we need for manipulation is the understanding of physics, understanding the physical interaction between your hand and object. There is very little data in the training of the LLM or VLMs, right? These are the text on the internet. These are the images, and some of these are videos. So there is nothing about the friction, the feel of interaction between the human and the objects. So I think that part is missing. Even though we have made a lot of progress in FSD, in navigation, but the detailed interaction in manipulation is not captured in the foundation models. This is why we need to get a lot of interaction data, physical interaction data, and use those to fine-tune your foundation model. So there's a slight difference there. Going back to locomotion, again, it's a physical interaction between your feet and the world. So it's slightly different from FSD. But I do think that the locomotion is reasonably solved problem now. It's not solved 5 years ago, but today, locomotion, especially blind locomotion, I would say it's solved. A robot can run, can jump, can parkour, can do all kinds of things, moving its center of mass in the world. I said it's blind locomotion because the combination of your perception and decide where to go, and then decide like how you should plan your footstep, that is not necessarily solved, because it's really hard actually to understand the raw pixel from what you see and then use that to guide your footsteps. So today, I think RL reinforcement learning mostly solve the blind locomotion problem, or tracking a trajectory like dancing while keep balance, not the detailed like a footstep planning. So for example, if you ask a robot to walk on stepstones, it is still pretty hard because you need precise foothold based on your perception.
I see. But does that really require complex understanding of the world? If you look at human animals, so basically you practice a combination of skills, right? And if your skills are like, okay, I know how to climb ladders, I know how to work in very sandy environment, then when I go to a new sandy environment, I don't even need to think. It's just basically I have this motor skills in me that I just pull it up. Just like driving, right? If I have a really wide tire and I can drive in snow in a new environment, just driving snow first time.
That's true. So if you first train a set of primitive locomotion skills on different type of terrains, then you have another neural network or the brain to decide which primitive skill I need to choose. Yes, that is a good construction of the problem. But the thing is, I think that the very few research or companies has go fully into that direction and combines the semantic understanding of the world. So this is sand, this is muddy, and then use that to make decisions on all kinds of primitive locomotion skills it can adopt at that scenario.
I see.
Yeah, if you look at the most impressive demos, probably from like a Unitree. It's a Chinese company that manufacture both quadrupeds and bipedal humanoids, and they are some of the early adopters of reinforcement learning. So they are really ahead in terms of hardware and control. You see, most of the demos are blind locomotion, so they can run really fast. They actually win the gold medal in the robotics, like a humanoid, sport competition in Beijing a couple of weeks ago. And then they have shown, dancing, but it's on a flat surface. They have shown like boxing, but there is no like very complex terrains in these cases. So combining perception and locomotion together in the wild, in the real world scenario, I still think it's an unsolved problem.
I see. But is that kind of where locomotion is easier than manipulation, in the sense your vision and your locomotion skills can be somehow separated and you can package your locomotion based on how human or animals learn it, right? I think manipulation is very clear, your hand and your
hand-eye coordination is
it's
closely
very
coupled.
important.
Yeah, I agree. I think that I worked in locomotion before, and I would hate people say locomotion is easier than manipulation. But now I get into manipulation field. I have to admit, yes, I think manipulation is way harder than locomotion, because in locomotion, I think there are basically two things: the geometry of the terrain, right? So these can be easily represented as a height field in simulation, and also the semantic information of the terrain. Are these tall grasses passable by my robot? I think that's it. You can do semantic understanding, make decisions, and then you can do low-level locomotion based on the terrain. But manipulation is way harder. The environment is a lot more diverse, right? You see, here is a kitchen, here's a table. I need to grasp a soap which is very slippery. I need to grasp this cup that has a handle. So I should not grasp in different ways. This is most stable way. And all these things need to be understood. And then you need to plan a grasp with your hand, which has a 20+ degree freedom, which is a very, very hard problem.
Yeah, I think hand is like people haven't even made the hardware of a hand to work, right? So it seems there's like a lot of different, and also people don't have sensors for very accurate kind of like the haptic response, and the force sensor people have something, but it's also not that perfect. So it feels like even hardware is not ready, data collection is not ready. I feel like the locomotion today, it's almost possible to make some robots that is as strong and robust as some of the good animals that can hunt.
So there's multiple things need to get into the right place, the right timing to solve a very challenging problem. If we look at why locomotion has made so much progress in the last 7 years, I feel that there are three things. The first one is there's a very powerful new algorithm that has been tried in locomotion that is reinforcement learning, as we mentioned. The second thing is you really need a way to do very fast iteration. So when I started the deep reinforcement learning on locomotion, we don't have great tools. And every experiment takes a couple of days because, as mentioned, it's not a very data efficient algorithm. So it takes like billions of steps of simulation, and it takes a few days. So every time you make a change, you wait a few days. So that's not efficient. But later, I think NVIDIA has made this Isaac Gym. So that's a simulator runs on GPUs. So you can simulate like thousands of robots simultaneously. That shrink your multiple days to 20 minutes. Now, every time you do an experiment, it's 20 minutes. So you really need that fast iteration to make progress in research. And the third thing is we are not just doing things in simulation. Otherwise, we go back to computer graphics. You really need to deploy it on the real hardware. Then the readiness of the hardware is the third component. I think locomotion is solved because of Unitree actually made these very, very cheap hardware that's very reliable. They were sold into the academic world, both in China, but also in North America. And then people can deploy their policy on the hardware, and every lab can afford to have the hardware. So these three things combined actually solve locomotion, or let's say make a lot of progress in locomotion in the last 7 years. But manipulation is different, as you say. We don't have great hand yet. I think the pioneer of dexterous hand is probably Shadow. And it's super expensive. And also it's not very reliable because of the tendons they can stretch and so on. But I also see that in the last year also, there's quite a few good companies come into existence. They tackle the hand, but it's still a very challenging problem because you need the form factor, you need the size to be similar to human hand. Then you need to put like 20 plus motors somewhere in the hand to mimic all the degrees of freedom the hand has. And then it also cannot be too heavy. Otherwise, your arm cannot drive it. And then you need a tactile sensing, not only on the fingertips, but also on the palms and other parts of the hand. So these technologies start to become more and more mature, but integrate them into one complete and reliable hand is still not there yet.
I see. Do you think this is gonna kind of be the biggest bottleneck, where when the hand manufacturer, let's say someone like Elon or whoever made a great hand, all of a sudden the field will go through the acceleration phase? Or you think there's like more to it, like we don't have enough of other things that even if you have good hardware, it will stuck for another 5 years?
My current feel is the hardware is probably the limiting factor for hand now. I feel that if you have a great hand that's cheap, reliable, have all the sensors you need, on the software side, on the algorithm side, we already have all the weapons we need to tackle this problem. We have reinforcement learning. We have some of the learning from human videos, so that there's a lot of the human video that has hand manipulation things. We can also have the teleoperation of the hand. Then we can leverage imitation learning. So we do have many paths that's promising on the software side, on the AI side, to make dexterous hand work, but the hardware is not quite there yet.
I see.
Yeah, often that in my team, people say, "Oh, I'm interested in dexterous hand." I will say, let's really look at the market of the hand, the hardware first, because I know that in simulations we can do good hand manipulation. But if the hardware is not there, maybe the timing is not right to do dexterous hand manipulation research.
Do you think the hand company will also be a pretty strong research company like NVIDIA that will ship this high quality simulation with like how friction works and all that? Or someone else can easily, that's like much easier problem. Someone else can solve it if someone just like focus on manufacture a high quality hand with like nice motor, nice tendon.
It's really hard to say. My gut feeling is the people who do hardware and people who do software, they might be two different companies, or they might be two different group of people. Because hardware is really hard. It needs like deep expertise. It needs a lot of focus, not only just the design, but also later, the manufacturing process. so that the hand is really reliable. They are consistent among different pairs, and then they are low cost, so that we can have the volume of the hand. So that alone is a huge problem. Then these group of people, if they can focus on this, I think that they can leave the other hard problem of the hand control of the learning to a separate group of people that has the right background to tackle.
I see. Yeah, just kind of like the NVIDIA and Unitree scenario.
That's right.
They don't do it together. The field today is still relatively more open than like most of the other field that has completely worked out, and people just guard the secret sauce because it's too much kind of business. Kind of if you get a few good researchers, it's worth like half year lead time, right? I think robotics somehow is still a more open field since it's not arrived to like, okay, if you figure out this, here is another $1 billion.
I see. I feel that yes and no. I feel there are still a lot of open source contributions to the robotics community, right? So many or most of the foundation model today, they are open sourced because we are still in a relatively early stage, as you say, the open stage of the research. But we are also making rapid progress. I would say that in the last year or so, the progress of robotics has really impressed me, even surprised me in a positive way. I would foresee that in a year or so, the field will gather more and more secret sauce, and more companies is going to be more close to keep their secret sauce. So that's my prediction.
I see. So I think it will go through the same process of all the big model training labs went through, almost like a shift from pure research organization to more quant trading firms that guard everything.
I think so. You can view it in two different ways, right? You can view it as it's less open, so maybe the whole community is not going to benefit from everybody talking to each other. But at the same time, it's a symbol of this field is progressing so fast, and then robotics is at the verge to being solved. So it's also the signal to you that we are going to leverage robots in near future. So it's both good and bad.
Yeah. Okay, that's cool. Yeah, we had a bet with a bunch of different friends. Like, when do you think a humanoid that can handle some of your home work can get into kind of consumer homes? Let's say on the like a Model 3 level price, and also like safe enough to coexist with your kid. So what's your prediction of the timeline of that? If you think there is rapid progress, love to see.
If you asked me this question 3 years ago, I would say it's probably been a lifetime. If I can see this within my lifetime, it will be great. If you ask me this last year, I would say maybe 20 years. So it's already, because of the rapid progress, I already shrink my expectation. If you ask me now, I think it's roughly in a 10-year horizon. So again, it's halved in a year. The reason I think it's still quite far away is because of there is a huge gap between the different stages of a product, right? So I think we are still at early stage research. We're still figuring out how the humanoid robot can generalize in a structured environment, how the hand can work, and all these things. And we start to see prototypes, right? So I think there's a lot of companies that show impressive videos or demos that the robot can do certain things for you at your home. But from the prototype, the next stage should be live demo. I don't see a lot of live demo yet of humanoid robots doing household things. So it means that the people still do not have the confidence that it will work 80% of the time. Even for a single task. Right? So there is a gap here, and that gap will take a while to bridge. And from that live demo to actual product, that's often way longer.
That's the hard.
Just to think about self-driving, right? 10 years ago, we feel like it's almost there, and even today, it's not fully landed. So there's a lot of things. Once you go to people's homes, safety is a big issue. Right? So AI safety is still not solved, right? Even the large language models hallucinate today. It might be okay for a language model to hallucinate. It's just annoying. But for a physical robot to hallucinate, it can do real physical damage at your home. And second thing is, people's home is so different. So unstructured. Your home definitely looks different from my home. Some home is cleaner, some home is messier. And generalization is still one of the biggest bottleneck that haunt robotics field today. So we really need to narrow it down. And progress is fast, but the challenge or the gap is still very, very wide. So this is why I say that I think that it's at least 10 years before a humanoid robot can come to your home and do a lot of useful things at your home.
Yeah.
But I do think that it doesn't mean that robotics adding value to the society need to wait so long, right?
Yeah.
So
totally.
it's just you are choosing the very extreme
that's the
case.
hardest stuff.
That's the hardest one.
Yeah. So I wonder, how would you project, let's see, for when you see the adoption curve, right? There's some technology in robotics that has got to the point that, okay, now it's the time that the technology is ripe, and it's like time to scale up mass production and stuff. I think probably like the robot dog with maybe something on top of it that does not do touch but can interact with the world is probably relatively ready stage. Like say move big things from A to B, combine the rolling wheels with walking around to go through tough terrains. Feel like those are ready. So how would you rank what will first get ready, and then what's the next thing? And in the end, it's probably like a household humanoid, right? What's your rank?
Okay. So as you mentioned that some of the form factor is more mature than the other. For example, robot dog is more mature than the humanoid. Some technology is more mature than the other. For example, navigation is more mature than manipulation. So my prediction is, many of the navigation tasks will be more automated. Originally, I think even today, a lot of navigation things already happen in factories, right? In logistics, they have these AGV that can move boxes in factories, in warehouse, and so on. But I do think that it will extend beyond the structured environment. So people often say last mile delivery. So it's a very challenging problem because the last mile can look very different for different address. I do think that these kind of things is going to get closer and closer rapidly towards us. So the navigation problem, if you don't need the interactions with your hand, with manipulation, these will happen first. And the second thing is, I think it will happen at a similar horizon, is companion robots. So these are robots that they get into your home, so unstructured environment. But they are not very useful in terms of manipulating objects, right? They are not going to wash your clothes or do your dishes, but they can talk to you.
Kind of tabletop robots, right? I can walk around on your table.
It's more than tabletop. It can also on the ground. So it can follow you. For example, it's a robot dog, small robot dog. They are cute. They give you emotion values. They talk to you. They can, play with your kids. They can do, easy like education things for your kids. It can, be a companion for, elderlies and so on. Again, because it, sort of get rid of all these complex things of manipulation, and it leverage the existing technology of language models. I think that these are much closer, and they also deliver values to the society. So I think it will be a promising product form. Then after that is really manipulation in a narrower domain. For example, there is a startup called Dyna. What they have shown in Coral is a conference on robot learning, is an impressive demo that it can fold clothes. And it can fold clothes continuously for a very long period of time. I heard that they are also working with Din Tai Fung to fold the cloth. So basically, it's a very traditional, very hard problem for traditional robotics, is that you have deformable objects, right? You want to fold it. But somehow using the VOA, Robot Foundation Model, and reinforcement learning, today this becomes plausible. And so if you are target at a narrower domain, a vertical, I think there's quite a bit of a product market fit. that you can find values for these robots. So narrow domain before you go to the more broad applications. So I think these are the probably three directions that robotics is going to land in the real world sooner than the humanoid at your homes.
Yeah, totally. Yeah, for the last one, it's very interesting. Actually, that's one of Moyan's like a PhD thesis. She worked on. She wanted to do kind of like 2D deformable objects, but start with kind of ropes, right? Like how to teach like one hand robot arm to tie those like different fancy knots of like. Like essentially there's knot series, there is planning, there is also like a control, and there like to simulate it, you need like a Lagrangian, that traditional method that takes 40 minutes to solve one step. So lots of fun stuff. It's interesting to see today people have made a tremendous progress.
Indeed, right? If you look at what's the most impressive results in the last couple of years for vision language action models, it's probably manipulating these deformed objects, right? So I think laundry is one direction. People can do, folding laundries very well. Even in some of our Aloha papers before, the Aloha robot can tie a shoelace, which is super hard. But through imitation learning, through foundation models, and through some of the RL, these kind of very hard problem in traditional robotics become easier today.
That's very cool. Yeah. So looking forward, I guess one thing I would curious, what do you see as the major breakthrough we need for like more general robots to work out, right? You published like a Gemini robot paper, like the 1.5, where you're like overlooking the future, or like projecting, okay, here are things we have already done, and here are things that are missing. But if you were lining up like a top 5 missing piece and rank the time, like okay, how challenging, or like which one would be solved first? How do you rank?
Top 5, interesting. Okay, let's see. I don't know whether I have top 5. I don't think that we have so many hurdles to go through.
Oh, that's good here.
Yes. So the first one is a definite data, right? So we want a robot to be general. It means that it should have seen a lot of the data or a lot of the world it will encounter after deployment. Currently, teleoperation is still the predominant way of collecting data. As I mentioned, that it will hit the glass ceiling soon because it's not very scalable. I think that how to leverage more scalable data sources, such as simulation, such as human video, such as sensorized human data collection, such as using maybe the video generation models to create these kind of data. You can use VO to create, robot doing things. And how to learn from these more scalable data sources so that we can break the barrier of data would be one breakthrough that is needed. Okay. The second thing I think we need to break through is hand. We discussed extensively about the hand. I still think that the gripper is very limiting, especially if it's in a home environment. You have all the tools like a scissor, like a screwdriver. All these tools are designed for human hand. It's so hard to use gripper to solve these problems. So we will need dexterous hand, multi-fingered, and we need reliable hardware, cheap hardware to make progress there. The third one is safety. We take safety really seriously because robots are very powerful, and especially after they pair with a very intelligent mind. So we have done a lot of safety research in terms of semantic safety. It understands what it can do, it cannot do semantically. For example, you should not put a toy on a everything that can melt the toy, for example. You cannot pick up the mug and make it upside down if there's a liquid in it. So there's a lot of semantic understanding of the world, safe, unsafe. Then there's physical safety, right? The robot is bulky, it's heavy. You need to understand that if it somehow falls, it's going to leave a dent on the floor. Or if it falls on a human, it will be really injuries. So how to make sure that the robot is physically safe? It all requires a lot of research. So even today, I think self-driving, the main focus is still safety.
Yeah.
I think for robotics, safety is even harder problem in an unstructured environment. So I think safety is probably the third dimension. I think breakthrough is needed. These are my top three.
Okay. Yeah, I guess just along the first one, which is more, to me, relatively solvable as like AI researchers, right? We can kind of reason about it. How much breakthrough do you think can be generated by a fast progressing video generation model, or in the future maybe a mix of video generation and understanding, and kind of like a GPT-4 level video model? If you think about like Sora 2, Veo 3 as more like GPT-3 level video gen models.
Yeah. I think a lot of data, I foresee a lot of data to train robots is going to generate by video generation models in the future. Some people even claim that it will replace simulation. Somehow I sort of agree with that, because if you look at the realism of these videos, it's amazing. And I drastically underestimate how fast this field moved. Let me tell you a small story. Like 2 years ago, the director of Wandering Earth, he came to the Bay Area. He was worried because he felt that the next Wandering Earth come out, I think it's like 2 years from now, he will be obsolete because all the video generation models is going to come into existence, replace him for his job. That was like 2 years ago, right? So at that time, video generation model isn't great. So I comfort him, said, don't worry. Right? So even though we are working really hard, video generation is a much, much harder problem. So I think by 2027, nothing really significant will happen, and you will still have your job. You are the best director for that. But if you look at the 2 years of progress, right, from Sora to Sora 2, and then Veo 3 and 3.1 and so on, you can see definitely I underestimate the progress of the field. And it's so much better. But still, I think one of the problems that we have with these video generation models is, so first of all, it can hallucinate. The physics is not quite right. But all these things are super important for robots. But I believe that all video generation teams are sort of working on some of the physical realism, not only the visual realism to some degree in their future milestones. So I think that if the physical realism is resolved and it can follow the action that basically you make it action condition. So you give it every frame, not only just a text prompt, but also if robot move this way, what's the next frame should look like. If these two things get solved properly, I think that a lot of data generated by these models will be very useful to train robot foundation models.
I see. So in this video gen model, do you see the decomposition we just discussed, the visual realism, like the gaming engine versus the physical engine that's simplified? Do you see there is a way to do this orthogonal decomposition? You can run very fast physical real, but simple visual stuff, and then you can make it both physically real and then like visually real, which makes the vision to control whole stack working as a simulation environment.
I see. I haven't seen it now. Maybe because of the visual realism just come for free. Right. So then people just try to augment the visual realism with the physical realism. So we don't need to go back, say that we don't want the visual, we do orthogonal physical, then combine them in some way. So if we already have visual realism, then we can add the physical realism. So why not?
Yeah, because the speed is not a problem here, right? It's around the same speed when you do like video generation.
It depends on how you use it. If you use it in reinforcement learning, I think speed is still a problem. But in addition to reinforcement, we now figure out more ways to leverage the data, right? Like imitation learning, you can offline call many of the generation models, generate tons of data, and use them as an imitation target. If that's a way you use it, I think that speed is not a big concern.
I see. So then the natural question is, do you see with this some technology similar to video generation? Do you see like do the generative physical sim, basically say, hey, like here is a physical model, try do it. Okay, you do reward hacking. Let me upgrade my physical model.
Yeah,
Here is a more complex one. Just like in the Matrix movie, right? You can slowly make your world more complex, add more gravity.
Yeah, I think a lot of the paths or innovation we made in simulation, as you mentioned, this co-evolution of simulation and policy is going to happen as well while you replace your physical simulation with your video generation models. I think they draw a very good analogy between them. It's just they are implemented in very different ways. Right? Physical simulation is about Newton's second law most of the time. Then you solve the differential equations. But the video generation model is more of a data-driven technique for that. But at the end of the day, their usage is very similar. They can use for policy evaluation. They can use for data generation. They can use for planning. So I believe that any progress we made in simulation, similar ideas can be borrowed in video generation to make it a world model to train robotics.
I see. And you think in the end, the two fields will roughly merge, at least for robotic purpose, so that, or you think there will still be like a kind of very okay, let's imagine 5 years from now, do you see there is a huge department of like traditional sim people still writing C++, differential equation based sim, or you think everything will be like a differential equation based sim work as more like a data generator for your like a video gen approach? And then
I think the latter will happen.
Okay.
Maybe people don't like it. People still want their jobs to write solvers for differential equations. But I feel that a lot of the simulation is going to generate. We already see it today, right?
Yeah.
The simulation not only just use in separation to train robotics, it's also generate data to train like video models, to train foundation models. So I believe that more of those will happen in the next 5 years, and eventually everything will be one giant model, right? It's a multimodal model that can take in text, audio, image, video, all the modalities. It will generate all the modalities like video and all these things, and the video will be not only visually but physically realistic. So eventually it will be one big model that can simulate the world.
Yeah, that's very cool. Yeah, so do you see that model output some kind of uniform robotic formatting that also sync with how you collect real-world robotic data from teleop or from like all the other ways that you collect real-world trajectory? Somehow there must be a standardization layer that you potentially can put your simulated robotic environment trace with like your today the most useful thing is still teleop, right? Like what is the space that maybe like what semantic level do you think that will look like that you can map the two in the same space?
I think that it's probably from the level we always say observation and actions. I think it's probably a similar level. It's the input would be observations like images and so on, but input also involves text, such as you express how you are going to what the robot is going to do, the task description and so on. It could be in the format of audio if you use the native audio to control the robot. And the output would be the actions. But what is the action representation is still a research problem. So some people say the action should be the joint trajectories. Some people say the action should be the end effector trajectories. Some people say it should be a learned representation of the actions. So that is not converged yet. I think there are still a lot of possibilities on the output side, what the action format look like.
I see. But input, it's clear, it's kind of similar to how human view the world. It won't.
At least from the trend today, yes, it's very similar to how we human perceive the world.
I see. Oh, that's very cool. So then it seems, if you do that really well, basically the low-level control, the RTX layer will be a much bigger bottleneck than the more like a CAN.
I agree. Right? Yeah. So today, I think the bottleneck is really on the low-level control side. It's not on the perception planning side. The reason is because the perception planning is all about the semantic understanding. It's all about the visual perception, and today's like a vision language models already capture those well because the training data covers visual, covers text. Text is the main way of doing planning and reasoning. But the low-level control is about physical understanding, physical interactions, and these we don't have a lot of data yet. So far, the low-level control is the bottleneck for robot foundation models.
Let's see. Do you see something like scaling law work in the low-level control field? Maybe like some type of RL or some type of like what is the axis that people scale to make like control policy better?
What do you mean by axis?
Like do you think it's much more compute or much better data or like?
So currently, I think we are bounded by data.
Okay.
So I think compute is fine because our data is very limited for the low level. I think maybe collectively the whole field gathered maybe hundreds of thousands of hours of data through teleoperation, compared to the amount of the image, video, and the text data on the internet. It's like a very, very small fraction. I do believe the scaling law will also hold for robot data. It's just we have not enough data to verify it yet. Once we have enough data, then compute might be the next bottleneck, but we need to really focus on the current bottleneck of data first.
I see. So when you talk to like data vendors and like also I guess simulation data like sellers, what are the things you look for, and how when you take them, how do you uniformly like evaluate like is this going to be useful? Like in quant trading industry, we have this practice like when some vendors sell us data, we have the like a smell test. And we run some simple machine learning model on it and say, okay, this potentially is useful. Let's buy a trial.
So it's very similar. It's very similar. It's we also get these data. We run small scale models and then try to deploy so that we have this closed loop to see whether data is good or not. We also have our like other metrics so that we have a little bit intuition like what to look for in the data, like the diversity, consistency, and so on and so forth. But I feel like overall the data quality is a undefined term in robotics. Everybody has some insights, but it's not an equation you can write out and can easily run it past all the data and then give you a number, then say good or bad. This is why that we have not yet started a large-scale involvement with different data foundry yet, because it's very easy to get into a scenario that they give you a lot of data, then you cannot train a good model. You will say your data is bad, and they will say your model is bad. It's an awkward situation. So we are still doing most of data collection in-house, and also leverage the data generated from Mojoko, which is also our team, the data generated by VO, the data maybe on YouTube. These are the things that we can iterate really fast to understand the data quality and how much data we need and how we can, move research forward to leverage these different type of data sources.
That's very interesting. So basically, it is kind of the skill AI for large language model age, right? Like we haven't.
But there's so many like
startups there
doing that now. I think it's right timing to do that type of startup, because I feel that data quality and data quantity is going to be figured out very soon. I think now is a good time to figure out the operations you need in order to collect such a large amount of data. So one advice I often give to the data foundry startup is you really need to be very nimble to adapt, to pivot, because of data has not been figured out yet. Today I might want tens of thousands of hours of teleoperation data. Then you can invest a lot of money to it, right? Buy all the robots and scale up operations. But then tomorrow I say, okay, our research shows that I want sensorized human data. I don't need teleop anymore. Then you can have a way to still survive that kind of quick pivot, because research are not done yet. And research needs fast iterations.
So at this point, probably even the data foundry's founder need to have almost a researcher background and have good taste and keep track of the field to see the breakthrough. Otherwise, if you are like half year late on realizing, the paradigm shifted, might be dying. It's like a high capex business, right? It's even more capex than like coding data.
That's right.
Okay. That's very interesting. I look forward to see how this field pan out. It feels like this will be one of the few things that will be a whole new like heavy investment field, since compute is probably going to join with the same kind of like compute requirement from the Stargate and all that. But robotic data is a very new field.
It's a new field, yes.
Yeah, it requires very different types of kind of data providers and large language models.
That's right. And also, it's so much harder to collect these data.
Yeah.
Because they don't have the flywheel.
Yeah. But even in coding, so far it's not using flywheel like a cursor is like selling data as the biggest vendor. It's still like a more specialized data vendor that is like basically do things per the request of researchers. So I suppose something like this will exist for robotics.
I think so, yeah. But the real way to, or the correct way of really collect large scale data is to build this data flywheel, right? So you have some product like Tesla. They have the car, so car is useful. People drive the car, collecting data. That data is getting used to improve the FSD. Then people use FSD more and more because its performance is better. But people still intervene, right? It's not perfect yet. And all the intervention data, again, help to improve the model. So that data flywheel is there. So this will propel the performance of these autonomous systems greatly forward. But in robotics, we don't have that data flywheel because a lot of these autonomous robots are not very useful yet. So now we pay people money to collect data. But that's not scalable. So we need to figure out the data flywheel ourselves too.
Actually, this is an extremely interesting topic. If you project the future of development, I can see two paths, right? One is the Tesla approach wings, where on robotics, someone that produce good hardware and scale up hardware that send the robots to people's maybe not home, but like a factory to like to ship delivery. They own the distribution of the hardware and they collect data. And then they train model, they rely on pre-train, the same way that Tesla win FSD today. The other approach is kind of like video generation, like smart researcher, infinite compute, but they do not own a real world kind of hardware distribution, teleop, and things almost work out purely kind of like how OpenAI wins, like at least GPT 3.5 before they have ChatGPT, which is a massive distributor and collect real world data.
Right. Waymo and Tesla, right? So Waymo have a very high goal from the very beginning. We want to do L4. So even though I don't really have my own cars, sell hardware, I do all the research needed. I partnership with different companies that provide the hardware. And then there's Tesla Way. They actually sell the hardware. They have the entire vertical. So they have the data flywheel from day one almost. And then they accumulate the data, improve the performance of their model and so on. There is no right or wrong. And it's still very hard to say which one will win. Because on the Waymo side, you already see that it operates in multiple cities without a safety operator. So basically, it's really driverless. And the Tesla, they are improving, iterating really fast, but it still takes some innovation to remove that driver from the driver's seat. So I think that it's very hard to say which way is the better way. It's more of your personal preference and personal belief.
Yeah, but I can totally see it's not possible that one company can do both, right? It's like it takes very different gene and operating capability to execute the different kinds. One is more like a Tesla style company. The other is more OpenAI or like Google style company.
Right.
So it's interesting. Yeah, I think one of the two will have a breakthrough and build the next.
I think these are just two very different paths towards a very common goal. Right? For example, our goal is solve AGI in the physical world. We can do only the AI part and then partnership with other hardware company to find the applications to build the data flywheel. Or we could do a vertical, we build our own hardware and find application ourselves and then iterate there to build the data flywheel. So I can tell you my personal preference. I don't speak for Google
of course,
Deepmind, right? So my preference is I feel for the analogy between robotics and self-driving is not quite precise, because in self-driving you already know it's useful.
Yeah.
There is one application,
Yeah.
clearly, so you can build a vertical in that application.
Yeah.
In robotics, which is the first application domain that will be useful is unknown yet.
Yeah.
Right? So you build a hardware, for example, you build a humanoid. Maybe it's not the first right form factor.
Yes.
So there's a lot more exploration needed.
Mm-hmm.
So my personal preference is don't do the vertical yet, and build something that we are good at, and then partnership with a lot of different companies to explore what is the right application.
Yeah, but I think the partnership normally ends up not as efficient, right? Like OpenAI tried to partner at public knowledge with 1x and then with Figure, but in the end, I think the vertical integrating in one company is faster as you guys collect data yourself. You do not want the kind of cross enterprise data wall or business wall.
Yeah, I agree. It's all the trade-off, right? So you can gain. It's not obvious, right? If the vertical integration is obvious, then everybody is going to do the vertical integration. It's always a trade-off. Then, as I said, it's your personal preference and personal belief.
I see. So Google used to have more like everyday robots and all that, which is more like leaning towards trying the Tesla approach. So right now, you don't see Google actually try to see, there is one vertical that it's clearly something that we want the data fly well and we want to build in-house. It's probably very hard to pull it off. Google is more like very high profit margin, like nice business in software land.
It's very hard for me to comment.
Yeah. But it's interesting that how the future can. Maybe I think it's in some vertical, the Tesla approach will pan out the fastest. Maybe like locomotion, dogs and stuff.
I agree.
Yeah.
So again, I think it ends up with personal beliefs, which way you would like to do and which costs you are willing to take.
Yeah. That's very interesting. Okay, let's come to our last question. Normally I have the transition and make a basically anti-consensus contrarian bet about the future for the next 1 year, next 5 year, next 10 year, like 3 bets.
1 year, 5 year, and 10 year.
And 10 year, like generally within robotics or like something tangential, like video gen, like a vision foundation model. Yeah, what's your 3 prediction that you think are contrary enough that most researchers today don't agree?
I think actually many things people have consensus on. It's actually very hard to find something that it's really controversial for a year. So my prediction is in a year, we're going to figure out to leverage different type of data sources to train robot foundation models. And I predict that the video generation model will be one of core source. Okay, so that's my prediction of 1 year. How controversial that is, I don't know. Maybe if you talk to Sergey Levin, he will disagree. But I think like if you talk to many other robotics players, many of them will agree on this.
Yeah.
In 5 years, I think that by that time we should have already passed the ChatGPT moment for robotics. So we in a limited scenarios, we have shown very general robots in unstructured environment. But I think that in 5 years, it's very hard to land humanoid robot in homes. So I think 5 year horizon, we probably have more specific applications, but the robotics should have already started to really deliver value to the society. And it's no longer a lifetime thing. People will change their belief and believe that the robotics is really coming. And 10 years, I think that they will enter everybody's home and become really useful in your daily life. And everybody should be sort of familiar with robots or in an adaptation stage of this new robotic future. Very similar to a lot of us are adapting to the AI era, like how to use ChatGPT or Gemini in our daily activities. And I think in 10 years, we are in another adaptation stage to see how we can work well with this robotics future.
Yeah. With that, thanks everyone for listening. Here is Jie and Bill. Thanks so much for listening to our podcast.
Thank you very much.
Bye.